So we'll continue on with a little bit of the electronic or atomic orbital shapes, but then we're going to get into electron configurations today. So by the end of today, you will be really good at all of your electron configurations, not just for the ground states, but also for the excited states. And then we have all of these rules or trends that we memorized from freshman chem, and we're going to actually dig into the data today to understand how we why we claim the rules that we claim. Things like half-filled shells are stable and so on. So again, we took this idea of wave mechanics in one dimension and extended it to 3 dimensions. And we have this oscillation of the spherical harmonics. We discussed this quite a bit last time with my hands, and that today I have some actual drawings. And so let's look at what these oscillations of the electron cloud look like. You know, when we draw an s orbital, with this L equals 0, we can look at what we mean by these colors. And so we draw the ball and we make it all one color. And what that is essentially looking like is when the cloud is expanding, say, we color it green. And then when it's shrinking, we color it red. So in time, you know, this cloud will shrink. Do you see the black line is its sort of average position, and the dotted lines are the extent at which it changes. And so it spread out to the dotted line and it was green, and now it's shrunk down to the inside dotted line and it's colored red. So over time, that s orbital blinks, if you will. You know, if we were to draw the colors over time, it would blink. But really, it's not blinking positive and negative charge. It's expanding and contracting. So that's what the positive and negative mean when we draw them on the orbitals. Okay. This next one is a p orbital, and if we have the black dark line is the average position, and the dotted line is its deflection. Notice it's deflected upward, and so we would call that part of the deflection green, and then we would color this bottom part where it shrinks red. And notice if we were to sit here and we were to plot this in spherical polar coordinates, so at this angle, it's changed 0 amount. At this angle, it's changed a little bit, you know, so just this little bit, say, let's just say it's 0.1, right? And then at this angle, it's about 0.5. And at this angle, it changes out by 1 unit, say. And then this would be -1 down here. It's shrunk in, and so at this angle, it would be -1. Notice how it gets big as you go up, and then it gets smaller again as you go here till it hits 0, and then it gets big but negative, and then it comes around and hits 0. If we were to plot this by angle, this is the shape we get. We get that dumbbell shape. So notice we then sort of make the length of that arrow or that plot along along this angle. We make that arrow. So like this arrow here is 1, and this arrow down at this degree is 0, and this was the 0.5. And if you think it goes from 0 at this angle all the way around to 1 and then back, that seems like a sine function, and this is a sine function plotted in terms of its angle around. So sometime later it oscillates down, and so then it expands on the bottom and contracts on the top. And so our p orbitals blink like this. Then here's an example of the d orbitals. So it expands out, it squishes out, and shrinks in at the waist. And then sometime later it reverses that. And so this pattern here we see with the d orbitals. Now I've just drawn it with little circles. It's not exactly that shape, but it's close enough. You can figure it out. And if you were to draw these things by hand, those little circles would be enough for you to figure out what's going on and what will mix with what and the symmetry of things. So here's those shapes of the orbitals that I showed last time going on up. These are the L and the M sub L numbers. Notice that the different row you're on is dependent upon the L. So L equals 0, L equals 1, L equals 2, 3, and 4. And then which one of those shapes you have is based upon the M sub L. For the L equals 0, we only have one of those. For the L equals 1, it goes from -L to +L, so we have 3 of them. for L equals 2, minus L to plus L. So we have 5, then 7, then 9, and so on. It's always 2L plus 1 options. We talked about the different shapes of the orbitals last time, so I really want to kind of get to the electron configuration stuff. We talked about how in a hydrogenic system, the energy does not depend upon the angular momentum quantum number, the L. I do want to reemphasize this, in case you missed it last time, that this is a Grotrian diagram. We're going to see more of these. And so those energy levels, and they're spaced by their angular momentum, S, P, D, F, you know, and it goes on to G, H, I think I've seen K, I'm not sure. It doesn't have an L column because that would be confusing. L is a quantum number, and so they skip a few things like that. But in multi-electron atoms, then the energy does depend upon the angular momentum, and so we see instead of the 2p being down here by the 2s, it's a higher in energy, and so we have this Aufbau filling scheme where you build up the electrons in order lowest energy first and move your way up. And so let's go ahead and finish this out. So let's do oxygen. How many electrons does oxygen have? Let's go to the periodic table. You see that number in the upper right. You know that. Let's review. Okay, inorganic chemistry professor was complaining. He said, my students didn't know what the atomic number was of an element. Okay, it's just a little tiny fact that you forgot what that name atomic number means. What is the atomic number of oxygen? Yeah, and what on there, what is it if you look at the periodic table? 8. Yeah, so 8 is the atomic number for oxygen, and it's the number of protons. And if it's neutral, that's the number of electrons. So you can look at that. You see the atomic number. If you have a neutral atom, that's the number of electrons. So we have 8 electrons. And so we just start filling these up. 1, 2, 3, 4. Watch this carefully. Everybody look up. 3, 4, 5, 6, 7. You remember that? Okay, you put them all, you spit them out. Now, why would they want to do that? And then you put the 8th one in there. So this is 1s2, 2s2, 2p4. Okay. But notice this 2p4 it doesn't have a lot of information in it. Drawing out the energy level diagram does. It shows that there's 2 unpaired electrons. Looking at 2p4, you'd have to think about it a little bit. But when you draw out the energy level diagram, you see that there's 2 unpaired electrons in that oxygen ground state. Okay, so why would we put electrons in individual M sub L's first before pairing them up? Yeah, they all have just 1 electron. Look back at, well, think about these p orbitals. There's one going along the z-axis. So let's just draw our coordinate system, x, y, and z. There's 1 in the y-axis, and then this is the hard one to draw diagonally. There's 1 in the x-axis in the back. If I put 1 electron in each of those orbitals, notice how they have an independent view of the nucleus. So that's going to be lower in energy. I could write oxygen as 1s, 2s, and then 2p like this. Okay, but this electron configuration would not be the ground state. It exists, but it's higher in energy. Okay, so what we're drawing with these is the ground state electron configuration, the lowest energy electron configuration. So those were the ones that you learned. But we're going to be talking about a lot of different ones in this part of the course where they're not in the ground state. And so this one exists, but this one's lower in energy. Okay, because again, the more independent interaction an electron has with the nucleus, the lower the energy of that orbital. And all these individual orbitals can have their own individual energies. And then you sum up the energies of all the orbitals and you get the energy of the atom, okay, or the ion. Let's do chromium. So chromium, we go up there, 24 electrons. Okay, 1s2, 2s2, 2p6. So we'll go ahead and add all of these up. 3s, 2. We're past the 3p row, so we'll put all of those in there. Okay, so we're finished with 3p. That gets us all the way to argon. So right here we're at argon. Okay. And we've used up, what is that, 18 electrons. So 19, 20, 21, 22, 23, 24. So that's how you would fill it out in terms of just following the Aufbau filling scheme. Okay. But look, this d orbital is got an extra space in it, and this s orbital has 2 electrons in it. I could give every electron its own independent interaction with the nucleus if I could scratch that one out and put it over here. Now every electron has its own wave function. It's not repelled by another electron in its same orbital, and so that's going to be a lower energy one. So this configuration is the lowest energy one. So it goes all the way up. I'm just going to say argon core. Do you see what I'm doing there? I'm getting us all the way up to the 3p6, and then 4s1, and then 3d5. Does that now make sense? I'm not sure if you'd covered that as your freshman level, you were like, I can't quite follow with these exceptions, right? But now it makes sense. We learn about orbitals, we learn about electrons. And if I could give that electron an independent access to the nucleus, then it's going to be lower in energy. And if I can lower those individual orbital energies, I lower the energy of the whole atom. Manganese is right next to chromium. And so I'm going to put one more electron into this particular electron scheme. Where do you think I want to put it? All right, so I have a choice. For manganese, I've got one more electron. I could put it in the 3d5. I could put it in the 4s. Does it matter? You're saying the 4s? Yeah. What makes you think that's a good idea? Yeah. And so, and also, I've got a nice, perfect situation where all of these M sub L's are all filled. There's one electron in each, and we'll see from the ionization energy data that that's a special situation. Whenever you finish a cloud, either with one electron in each or 2 electrons in each, that whole cloud has got like a stabilization situation. And so we're able to fill up the 4s and make it a completely filled orbital. That stabilizes that orbital. So this is going to be the manganese one. Argon, 4s2, 3d5. So practice those on your own. You can look them up online. Just work through the whole periodic table. In fact, there's a key here. This is a good key. It kind of gives you the general scheme, but you can find periodic tables online that have all of the electron configurations, and you should be able to kind of look at where the element is, like selenium here, okay? Selenium, you just go back and you say, okay, argon core, and then we enter over here on the 4th row. So I see that 4. That's where my selenium row is. I see that 4. I know the next one is a 4s. Okay? And then on that 4th row, that's where the 3Ds show up. And so then I have 3D, 10, and then I'm at 1, 2, 3, 4. So 4p, 4. 4th column. Yeah. And so you should be able to generally pick any spot on the periodic table and go there. Okay. And this idea of using these cores really saves you a lot of effort. Okay. Like say I do uranium. Okay, here we are, uranium. You know, that's 92 electrons. Are we going to start with 1s? I'm not. You can if you want. You get your paper out and your pencil sharpener. Okay, so I'm just going to go back. Where does this row show up? It shows up right here. And so we go back to the previous core. So that's the radon core. So uranium, we have the radon core. And that saves us what is it? I can't see. 86 electrons. Yeah, so we've got 86 electrons taken care of there. We have 92. So then we come in at 7s. Okay, and then we're going to go, this is the 4F, and this is the 5F. So 7s2, and then 5f3. So that's a good initial guess. That might not be, because the F's and the D's, when you get that far out from the nucleus, they might switch around, you know, but that's a good initial guess at the electron configuration for uranium. Okay. All right, so let's look at the evidence behind some of these things. I said that a fully filled subshell was stable and a half-filled subshell was stable. And this is where we get those kinds of trends. This is where we see those trends. So first off, let's make sure we understand what the E1 energy is. This is the amount of energy it takes to ionize the atom and make it a cation. So a +1 cation. So how hard does the atom hold on to that electron? So this is going to tell us something about the stability of the nucleus, the stability of the electron cloud, and the stability of those orbitals. So if it's really hard to pull the electron out, then it must be a stable atom. What would hard to pull the electron out be? It would be a high ionization energy. So notice it's really difficult to pull that second electron off of helium, okay? Because it's got that fully filled subshell. It's a noble gas. In fact, look, all of the noble gases are the highest ones to ionize in their little region. And that makes sense, right? They don't react with things because they have a stable electron cloud. All the other atoms want to bond with other atoms because they can make a stable compound, and the compound is more stable than the atom. But in the noble gases, that electron cloud is so stable, it'd rather not react because it's going uphill. The atom's down in sort of a well, and to make the compound, it's uphill energetically. And so it's just going to roll back down and form separate atoms. So let's look at some of these trends. And so this is some memes I found online just for grins. Okay, how they really made the periodic table. It's Tetris. And then the copper or chromium, you know, that Tom and Jerry, I don't know if you're a fan of that, but 4s has 2 electrons, and then 3d9 comes along and says, I'll take one of those, please. And then the Drake here, he's like, yeah, 4s1, 3d10. Okay, so let's look at some of these trends. So trend 1, the first ionization energy decreases with the size of the atom. We're going to go through that evidence and show how all of these trends come about. Okay. Trend number 2, the first ionization energy increases across the row of a periodic table. So going from left to right, the first ionization energy should increase. Trend number 3, the first ionization energy is unusually high from a fully filled subshell. That's your noble gases, but also the group 2 elements. Those have fully filled s orbitals. And the 3d10, zinc, cadmium, mercury, that's a fully filled d subshell. And then the first ionization energy is unusually high from a half-filled subshell. Help me find on the periodic table the ones that have half-filled subshells. What's a subshell? An S, a D, a P, an F. Those are subshells. So, you know, the P1 through 6, a half fill would be a P3 because it can hold 6 electrons. A D is 1 through 10, half fill would be D5. So help me find the columns in the periodic table that are half filled subshells. Just call out the top atom. Nitrogen. Yeah, so the nitrogen group is a half filled P subshell. So this is saying that every element under nitrogen ought to have a little higher ionization energy. Okay, what about the D group? Manganese, yeah. And then the S group, really the alkali metals. This is 2 in that group, so the first one's half filled. We don't really see much on that trend, but the D's and the P's we see. And then trend 5, the ionization energy is unusually low from a subshell with only 1 electron in it, or a subshell that is 1 electron past being half filled. So let's find the first one. Which groups have only one electron in their subshell? Yeah, group 1. So all of the alkali metals. If I take that electron away, what does the electron cloud look like? Noble gases, right? So those are really easy to ionize because I take one electron away and I have a noble gas electron configuration. What about what's another group that has just one electron in its subshell? Group 3, okay, on that numbering up there. So that 3D1, those or the scandium, yttrium, lanthanum, actinium. Okay, so that's the D1 group. What else? Boron group. Boron group is something P1. 4P1, 3P1, and so on. What about the one electron past half filled? That's a really weird situation, but we figured out the half filled ones. What's the next column over? Yeah, so iron. Little easier. Iron should be a little easier to ionize than manganese. Okay, because if I ionize iron, then I have the manganese electron cloud. And then what over there in the P group? Oxygen group. Oxygen group has one electron past a stable setup. So nitrogen's really stable. I add that one extra electron. Oxygen should be easier to ionize than nitrogen. So here's the data. Let's go look at it. We just talked about nitrogen and oxygen, and look. So remember, going up is harder to ionize. So nitrogen's harder to ionize than oxygen. And so this is the data that actually told us those trends. But let's go through this in general. So first ionization energy decreases with the size of the atom. We see that. So as the atoms get bigger, what happens to those frontier electrons? We're only pulling the last one out. They are so far from the nucleus. The only reason they're on the atom is because they are attracted to the nucleus, but it's easier to pull an electron off a radon than it is helium. Helium is a tiny little ball at 2 electrons, and you're trying to take one of its 2 electrons. And it says, hey, I've only got 2. Okay, but radon, you pull that electron off and it doesn't even know. It's like, oh, I'm charged? I had no idea. So that's just based on the size of the atom. We're getting those electrons way far away. So helium, huge difference in the energy levels between the neutral atom and the cation. So look what I'm drawing here. I'm drawing the electron configuration for the neutral atom and the electron configuration for the cation. Okay, do you see that? So 1s2, 1s1, and look here, radon 6p6 and 6p5. I've got the ... just to show there's all this in front of it, and then it ends in 6p6 and 6p5. Okay, but I'm really emphasizing that the quantum number n here is, from n equals 1, really small, close to the nucleus, n equals 6, way far away from the nucleus. Okay, the first ionization energy increases across a row in the periodic table. So what are the rows in the periodic table? That's these groups here. You see how they increase across the row? So from this data, we make that trend. I told you the trends first, but I'm showing you the data behind the trends. So from lithium to neon, we see, in general, the ionization energy increases across that row. There's a few exceptions. Look there's an exception there, and there's an exception there. And we're going to talk about those exceptions because those are other trends that we see. So down here, lithium. Why is lithium so easy to ionize? And look closely. I'm drawing this dotted line to show where that cation level might have been, but because it's an S2, it's stabilized. And so it's been stabilized, and that makes it lower in energy. Whenever you stabilize an energy level, you make it lower in energy. And so if we lower that cation energy level, notice how this arrow gets shorter. This arrow here is what's actually being plotted. That's the energy difference. And then neon up here, again, we have this fully filled shell. We have the 2p6 going up to 2p5 for the cation. And I'm going to draw the dotted line here to show that it was the neutral atom that was stabilized, right? So this dotted line shows where without this stabilization energy, if you want to call it that, you would have the ionization energy, because we're just pulling an electron away from a positive charge, right? If that's all it was, then the first ionization energy would be the same for every atom. So what's causing these differences is stabilization energies. We either stabilize the cation or we stabilize the neutral. If we stabilize the cation, then it's easier to ionize. And if we stabilize the neutral, it's harder to ionize because the neutral atom is lower in energy. So that would make this arrow longer. So we'll do lots of these, and you can get some practice. Now let's look at this. The first ionization energy is unusually high from a fully filled subshell. So we know the neon, argon, krypton, and all of those are fully filled, but we also have the beryllium group. See beryllium down, and then zinc group. So we have the noble gases, those are fully filled, but we also have the group 2 elements, and we have the D10 elements. So zinc, cadmium, and mercury. You see how high those are? They're almost up there with the noble gases because we have that D10. We have a fully filled subshell, and those are pretty difficult to ionize. So we stabilize if we have a fully filled subshell in the neutral atom, that neutral atom is stabilized. When I say stabilized, that means that energy is lower than we would expect, and it makes the ionization arrow longer. For boron, it's easy to ionize because the cation is stabilized. See, I'm drawing the dashed line and the down arrow anytime I have a fully filled subshell. If the fully filled subshell is on the neutral, then it's harder to ionize. If the fully filled subshell is on the cation, then it's easier to ionize. And then here we have neon. Again, that neutral has got the fully filled subshell, so it's become harder to ionize. Okay, then a half-filled subshell, where do these show up? That's the nitrogen, and then phosphorus. And then as you get farther and farther away from the nucleus, it's kind of the P group, trend kind of falls away. The next one is arsenic, and it still shows a little bit of this anomaly of stabilization. And so once again, this half-filled subshell we say is stabilized, so we're stabilizing the neutral. So it makes nitrogen harder to ionize. And for oxygen, the half-filled subshell is in the cation. And so we've stabilized the cation and made it easier to ionize. Does everybody see which levels I'm calling stabilized, right? Wherever that 2p3 is, that level was stabilized. And that made this black arrow longer. Over here, the cation was stabilized and they made the black arrow shorter. So it made it easier. And then when you go past that subshell, fully filled, or past a half-filled subshell, things are easier to ionize, and that's these oxygen, boron, and then all the alkali metals. And so once again, those cations are stabilized, and so it makes those black arrows shorter. Last trend, and this is, we're out of time, but let's finish this up. This first ionization electron comes from the s orbital for D and F block elements. So here's a Grotrian diagram, an actual one from the NIST database. And so for xenon, we typically have this, if we were to fill it up, if we were to do mercury, we'd have xenon core, 6s2, 4f14, and 5d10. And we would write them in this order according to the Aufbau filling scheme, 6s, 4f, and 5d. But these are the electrons that actually get ionized or moved around. And so the cation for mercury, that electron comes out of the 6s, not out of the 4f or the 5d. It took so much to stabilize those orbitals, the way I think of it. You know, we had got 14 electrons to oscillate together in this subshell. It's much easier to just pull one out of the s orbital, and then we still have a half-filled subshell for that s. And so that's going to be a more stable cation than pulling an electron from the f or the d. Okay. So that's our last trend. All right, well, we'll see you next time.